Hello everybody, and welcome to the latest edition of the Physics Corner, a series of videos in which we set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today we're going to revisit the problem we took care of a little bit earlier in a different episode, that of a rock falling from rest, or in other words, the law of falling bodies. Now, in that particular episode, we solved for the speed of a rock that was dropped from rest as it hit the water using what we call the equations of motion. We're going to do the same exact problem and, of course, hopefully get the same result, but using a different method. And that's the purpose of today's episode, is to show there's more than one method to solving physics problems. Specifically, we'll use something called energy conservation. So let's get started. In this particular episode, or this particular situation, our child is standing at the edge of a bluff or cliff and is holding a rock that is a height h above the water surface. The bluff is itself overlooking a lake, and drops a rock from rest. The rock hits the water surface at a speed v. What is the speed of the rock given a certain height? So let's write down what we know and what we don't know. So we always, as usually, assume that little g will be equal to 10 meters per second squared. As we like to do, we round it off for simplicity for our demonstration calculations. In this case, we have a height. So height in this case is 45 meters, like that. All right, so that's what you have there. Okay, what else do we know? We know the initial velocity is 0, so let's write that down like this. We can also say we don't need to write down an equation for it, but this is a one-dimensional motion problem, so the rock is dropping straight down. It also states in the problem that the air drag is negligible, and we can also therefore assume things like wind and such also don't count enough to matter. Okay. What don't we know from this problem? Specifically, we do not know what the speed of the rock is as it hits the water, and we also don't know what the mass of the rock is. Now, back when we did equations of motion, we found out, or we didn't talk about it actually, we didn't use the concept of mass. And we'll see if we need to use the mass of the rock here today or not. Let's go ahead and set this up. So let's do this in this new method of energy conservation, and then compare it to what we used to look at with equations of linear motion. So in energy conservation, we can write an equation or a formula that looks like this. This states specifically that the energy going into a situation, for example, the amount of energy possessed by an object or a system of objects to begin a process, is going to remain the same. It will be the same amount as the total energy at the end. Now, that does not mean we can't trade the energy back and forth into different forms. In fact, that's sort of the point. But the total amounts will be the same. To be fairly honest, by the way, it's not just at the beginning and the end. The total energy is exactly the same throughout the entire process. But let's take one thing at a time. Let's take a look at just what the energy is at the bookends, shall we say. Okay, so also, this begs the next question, and I already hinted at it. If there are different forms of energy, what forms of energy might we have in this particular problem? Well, one kind of energy is called gravitational potential. And in a lot of textbooks, including the ones that we use at Southern Miss, the potential energy formula, or potential energy abbreviation, is PE. Now, I will say that if you use other textbooks, or if you go to, say, different levels of physics, they often will not use PE, they'll use some other symbol, but in this case, the intro books that we use, we like to make it obvious. The G is a subscript that stands for gravity, so potential energy due to gravity, right? And that formula is mgh, which means the mass of your object, the acceleration due to gravity, and the height, right, like that. Another form of energy that we'll encounter, or you are starting to encounter now, is called kinetic energy. Now later on, we'll know that's specifically something called linear kinetic energy, which is straight line kinetic energy. We don't need to worry about that quite yet, but let me go ahead and write this down. So kinetic energy, and kinetic energy is energy of motion, and its formula is 1/2 mv squared, like that. Okay. So a half times the mass of the object multiplied by the speed of the object squared. Now, something that should pop out from all this is that this is or energy in general, is what we call a scalar quantity, right? And one of the ways you can tell, mass is always a scalar. It's always just an amount of something. And the v here, even if the velocity has a specific direction, when you square a velocity, that takes away that directionality. That no longer is part of the situation. So this quantity here is a scalar. It's just an amount. In other words, it doesn't depend upon which direction you're going to talk about kinetic energy. Now, in practice, of course, it matters very much which direction you're going, but that's not what this is talking about. Okay. Now, to get back to the problem specifically, though, why introduce these two and why talk about them? So, what's the energy going into our situation? All right, so up over here, our child is holding the rock at rest. At rest, as we all know, means that there's no speed, no velocity. If there's no velocity, there's no kinetic energy. So nothing of that is present. On the other hand, the child does have the rock a height above the water surface. So we do have gravitational potential. Now, also to make it clear, when we measure gravitational potential, we need to define where we're measuring from. What height are we starting at? In this example, it's the easiest thing to do is to set the zero level, if you will, at the water's edge, right? The surface of the water. And that way, any height above it is a positive height. Okay, so that's exactly what we're doing. So that's what the height is. So this energy equation here, we have potential energy due to gravity to start with. Now, at the end of the situation, at the end of the process, the rock hits the surface of the water. It now has achieved a speed, right? So it now does have kinetic energy, but just got done saying this, the height is 0 at the surface of the water, so there's no more potential energy. It's now all turned into kinetic. So this beginning formula here has been adapted into this specific situation here like this. And then, of course, if we write out further for the individual formulas, now looks like that. Okay. So let's go ahead and solve it. And this is it, by the way. We don't have any more formulas or anything else to add to the situation. This is as complicated as it's going to get. If you look at both terms, mass is common to both, and as we know, we can divide mass out like that, and it no longer appears. So we have this relationship. Let's go ahead and solve this quick. So let's multiply both sides by 2. So I can move the 2 over, the 1/2 over to the side, and let's take the square root. And that's the result we get there. And now it's time to plug in our numbers. So 210 meters per second squared and 45 meters, like that, right? Okay, I've chosen numbers that are easy enough that we can do without a calculator, but of course, if you want to tap one, you're free to do that. 45 times 10 is 450. 450 times 2 is 900. Square root of 900 is 30. And so the speed of our rock as it hits the water's edge, the surface, is 30 meters per second. This solution here, this V equals square root of 2gh, is very common. You'll see this crop up in several different places. And it shows up in a lot of situations where you're essentially dropping an object or even a system, even pouring water, for example, from a height onto a surface. And you simply get this solution because it's the same kind of process. Now, let's compare this to the equations of motion that you might have used to solve this way back at the beginning of the course. So in maybe the second week of the class, perhaps, roughly, you learned there are several equations of motion for 1D motion, and one of those equations might have looked something like this. So you would have Vf squared equals a V naught squared plus a 2a delta y. Now, I'm going to use delta y to stand for vertical distance. Okay, if you want to use delta x, that's perfectly fine. But I'll use delta y. I've done that before. All right, and this is what we did before. So let's take a look at this. Now, in this particular equation, we know that the original velocity is 0, so this term disappears. We also know that this little a here is really due to gravity, so we have that. And so if I rewrite this equation, it becomes Vf squared equals 2g delta y that way, or square root Vf equals square root of 2g delta y like that. And here's what I want you to look at. even though we've used slightly different symbols, the equation that we came up with using different methods is the same thing. So what we're showing here again is that there's more than one way to solve a physics problem. Quite often. I mean, sometimes there's one way to do it and that's it. But usually there's more than one way to get at a problem. And energy methods, which you're starting now, is one of those other methods. And so once you learn what energy conservation is all about, you can kind of appreciate what its power is. And this is an example of that. All right, everybody. Technical support for this program is supplied by Cindy Galchow and Sophia Turner. Funding comes from the University of Mississippi and University of Southern Mississippi. This video is filmed on location in Hattiesburg, Mississippi. I'm your host, Dr. Christopher Cirola. Thank you for your attention, and clear skies, everybody.